Smog, a portmanteau of the words smoke and fog, is an air pollutant that drastically reduces visibility. See the pictures from Wikipedia that show the same landscape 10 days apart. While smog was formed initially from the particulates in the incomplete combustion of coal, better combustion control and better scrubbing have reduced coal-fired power plants as a source most of the time and in most places. There are notable exceptions. Anytime a coal-fired power plant needs to ramp up, which often happens when a plant is fired up in the fall for heating or if the fuel supply is inconsistent, that coal plant will not burn as hot, which means it won't burn as completely, and that means much more particulate is formed. Incomplete combustion also accounts for carbon monoxide production, another smog-forming pollutant. On the other hand, other smog-forming pollutants, like nitrogen oxide species, NOx or NOx, and various sulfur oxides, are necessarily a product of anything burnt, whether complete or not. By law, exhaust must then be scrubbed to remove these vapors, which form acids when combined with water vapor, and so form acid rain. In addition to combustion products, certain organic molecules like alkenes, aldehydes, and peroxides all can react to contribute to smog, as well as can ozone. I've got some good news there. In 1970, the United States passed the Clean Air Act, which mandated the U.S. Environmental Protection Agency, or US EPA, to develop standards for clean air. The 1990 amendment to the Clean Air Act allowed a phase-in to reduce emissions of sulfur dioxide and nitrogen oxides using a cap-and-trade system, the first U.S. system to develop a limit on emissions and allow the market to trade around to figure out how to fall within that limit. You can probably see that the phase-in wasn't immediate, but we've been slowly decreasing this type of emission over time. This graph from the EPA paints a pretty rosy picture, around 90% of emissions from the 1995 levels. So the problems with coal fire emissions are solved, right? The problem is that 7% of a very large number is still a very large number. This data is taken from the Global Energy Monitor, who in turn cites the data made publicly available by the Energy Information Administration, a US government administration. This shows the number of plants with capacity over 100 megawatts that fell within a certain scrubbing range in 2005. This is still a lot of coal-fired power that doesn't have any scrubbing at all. So some of the decline in sulfur emissions may be from scrubbing. Some may be from burning coal that has less sulfur to begin with. But my guess is that most of the decline is from cheap natural gas power plants replacing coal power. It's expensive to remove the top of a mountain and transport a solid, while natural gas is a byproduct of fracking. And also anaerobic digestion in landfills and on large farms. It can even be transported by pipeline from those locations. But the narrative of we're not making sulfur oxides is not really true. On the same EPA website, just a little farther down, there's a graphic that shows sources of sulfur emissions. Note there are significant improvements in some of the largest emitting sources. The big dots get smaller, but there are more sources 30 years later, and the problem hasn't gone away. Emissions of nitrogen and sulfur oxides matter locally more than they do nationally, because these emissions combine with water and usually precipitate locally. But under certain conditions, they can actually raise to very high levels. Around each of these dots is a community, and you can probably guess what each of these communities looks like. The places where there are still significant emissions from power plants are where the poorest people live because they can't move. So when we make choices about how we use energy, we're making choices about how we're treating the poorest of the poor. And in many ways, the tale of an incinerator is a similar story. An incinerator burns fuels, and depending on the amount of sulfur, nitrogen, or toxic metals in these fuels, and depending on the heat that the incinerator runs at, it may or may not release significant amount of pollution into the atmosphere. But this isn't the tale of just one incinerator. This is the tale of two incinerators. The incinerator in the top left is in Robbins, Illinois. I live just upwind from it, which turns out actually matters for this story. The incinerator on the bottom right is in Kent County, Michigan, which incidentally is where I used to live. That also matters for this story. The incinerator in Kent County has been around for a while. It's been operating since 1990. This graph shows how the emissions from the Kent County facility compare to federal standards. For full disclosure, these are again percentage relationships. These are good, they're well below the federal standards, but they're not zero emissions for mercury. They're not zero emissions for lead. Combustion is not a zero emissions technology. However, the Kent County facility is probably meeting temperature targets shown by the relatively low level of dioxins and carbon monoxide and particulate matter, which are all higher when the plant isn't running high enough or hot enough. Part of the contaminant levels are based on effective scrubbing. This is an operator side responsibility. The operator needs to fight for the best scrubbing equipment and have well-trained operators to keep those levels low. The other contaminants are also affected by the purity of the fuel stream. So very little mercury is expected in the emissions if there's no mercury in the feedstock. Very little HCl is formed if there's little chlorine in the feedstock. So this is actually a personal level responsibility. People need to be careful not to throw hazardous chemicals or electronics waste into the trash that's going to get incinerated. Kent County probably benefits from an existing culture of waste separation, in part driven by the high bottle deposit fee. Every carbonated beverage container requires a 10-cent deposit that's returned to the customer when they return the bottles to be recycled at the store. This can add up pretty quickly, so it incentivizes a pattern of good waste management from the start. This facility is likely well run and poses minimal risk, and it continues to operate after 30 years. It's worth noting, though, that even though this incinerator is probably well run and poses minimal risk to the community, the people who bear that risk are those in very close proximity to the incinerator. You can clearly see that the people who bear the risk of any pollution of this plant are those who are poorest, and generally not white, looking at the figures shown on this slide. This is an important thing to keep in mind when we think about how we care for the poor. This is the same graphic for that Robbins incinerator, where the conflation of race, income, and environmental justice is even more stark. This power plant has a complicated history. The potential pollution of Robbins incinerator is a microcosm of a larger phenomenon. On the left, you can see which areas of the city of Chicago have the most environmental burden, with red being the highest burden and blue being the lowest burden. If you look over on the right, you can see how the racial demographics change in different areas of the city, with some areas being predominantly white, others being predominantly black, others being predominantly Hispanic. And hopefully you can see that some of the areas that have the highest burden environmentally, in fact, most of the areas that have the highest burden environmentally are the areas where minorities also are in the largest percentage of the population. The most industrial corridors are placed in the lowest income areas. The reasons are complex. Sometimes the jobs are welcomed by area residents, despite the risk. Sometimes the residents are too busy working multiple jobs to pay attention. Sometimes the voices of potential profits can drown out concerns. The linked LA Times article suggests that the Robbins Township elected officials, desperate to bring jobs into a low-income neighborhood, actually courted incinerator companies. They asked them to come, and they cultivated an agreement that involved jobs and scholarships for local students. Many of the opposers were from outside, but upwind of Robbins. For example, if you look really closely for a red box in the otherwise low environmental burden area just north and a little east of Robbins, you can see Robbins in the kind of blue circle. You can actually see my house. Beverly and the other neighborhoods that are nearby and other nearby towns were incredibly active in opposing the incinerator. Eventually, the opposition from affluent neighborhoods led to these neighborhoods refusing to send waste, let alone well-sorted waste to the incinerator. Burning incinerators with insufficient fuel creates more pollution, and these same neighborhoods that refused to send waste also successfully lobbied for a repeal of state incinerator tax incentive, which left the $385 million facility in Robbins unprofitable. It shut down in the year 2000 and remains vacant now, 20 years later. A quote from the article: "Everybody got all in an uproar when we said we wanted to bring Foster Wheeler in here, the operator of the plant," said Robbins Mayor Irene Brody, a soft-spoken but blunt woman who lobbied for the incinerator. "They said it was bad for the environment and all, but She paused for a second, then continued resolutely. "Didn't nobody ever come out and protest the fact that we're poor? How come nobody ever protested that?" So what was the right thing to do here? Almost certainly, a well-run facility with proper scrubbing would have an environmental burden that's overshadowed by the existing burdens in the city. And aside from Robbins, which stood to benefit enormously from the incinerator, most of the environmental burden would be borne in areas of Chicago that already have the lowest environmental burden and the most affluence. This is an incredibly complex issue that involves scientific best practices and a whole mess of human brokenness. That environmental racism exists is incredibly clear. Again, just match up the most polluting areas on the left to the racial demographics on the right. Regardless where someone might fall on the policy side of how the incinerator is placed, the science of combustion and smog-producing pollutants is clear about how to run such systems well. And I think that's something that was missed by well-meaning community advocates. The very act of refusing to send trash to the incinerator meant that it was harder for the incinerator to run at the appropriate temperatures. The company itself should have had provisions for supplementary fuel, and policymakers probably should have looked to actual particulate and sulfur oxide and nitric oxide concentrations as they weighed community concerns. If those who are concerned lived outside the impact range, the solution may actually have been about education instead. So how do we actually detect things like nitric oxides and sulfur oxides? Well, with spectroscopy, of course. That's what this 10-minute lead-in was for. More specifically, with quantitative infrared spectroscopy. Each of these gas phase molecules can be easily detected based on characteristic absorbances within the infrared range. We can measure most gas phase molecules using this method. When we start looking, we might actually find that there are all sorts of other sources of smog-making compounds. So we know that certain compounds cause smog, but what actually is smog and why does it form more in certain areas? Smog is formed because a number of particles, but particularly the particle nitrogen dioxide, react with sunlight. Notice that H nu up on the top of this figure that indicates the energy from sunlight, but this is a radical reaction which produces atomic oxygen and nitric oxide, that is NO. These are both radicals which will react with all sorts of other compounds. Because they have an unpaired electron, they're more reactive. That includes molecular oxygen, which makes O3 or ozone, and it also includes hydrocarbons, which can also be light reactive and can also regenerate nitrogen oxide. Notice that many of the products cycle and make more nitrogen dioxide or ozone that will continue to react. So once nitrogen oxide levels reach a critical mass, the smog can actually be pretty self-sustaining for some time, particularly when there are also many reactive hydrocarbons. These reactions take place in the lowest layer of the atmosphere, the troposphere. That means the highly reactive radicals of smog can react with most living things that don't live underwater. That makes the ozone formed here decidedly different from the ozone that forms from oxygen in the much higher stratosphere layer. Up there, it's helpful because it absorbs most of the UV cosmic radiation. So ozone up high, good absorbance. Ozone low is actually formed from absorbance of nitrogen dioxide, and it usually produces things like asthma. The presence of many types of smog-forming contaminants is time-dependent. Nitric oxide, the NO, is often a primary pollutant and can react to form NO2, which then absorbs visible light and creates more atomic oxygen and also ozone. We can think of the ozone as the primary oxidant in this system, which is shown in the thick black line. Let's start by thinking about that line. Under normal conditions, that oxidant, the ozone mostly, appears just as nitric oxide, or NO2, begins to react with light to form atomic oxygen and that ozone. So it makes sense that the oxidant pollution would be higher during the day, since it needs light for the oxidant to be formed, and light happens during the day. On the other hand, the NO line goes steadily up until the oxidant starts appearing, that big thick line again, the ozone. That's because the NO reacts with the oxidant to form nitric oxide, NO2. So the NO goes down as soon as the oxidant starts appearing, but then climbs back up at nighttime when the oxidant isn't being formed, when we're not making ozone. Similarly, nitric oxide, or NO2, peaks rapidly as the excess nitrogen monoxide, or NO, is converted into nitrogen dioxide. So that's why that dotted line for NO2 peaks really early in the day when light starts showing up and then falls down to a steady state. The NO2 falls quickly again as excess NO is used up. Now we can also look at non-methane hydrocarbons, the top line. Those peak with humans waking up and starting to drive their cars, with incomplete internal combustion engines as the major source of these molecules. But even though people keep driving their cars all day, those hydrocarbons are oxidized by ozone and other oxidants to form aldehydes, peroxides, and other reactive oxygen species, which is why you see the aldehyde line peaking as the hydrocarbon line is falling. It means most of the dangerous oxidative stress of smog is during the day when my kid's out on the playground. Two things I hope you got from the discussion so far: that nitrogen-based emissions and other smog-forming emissions are a cyclic problem, and that how long they last depends not just on the amount of nitrogen pollution, but also on the amount of other hydrocarbons. A third factor that really matters is location. Because the concentrations determine the half-lives of smog-forming pollutants, areas that are upwind of other polluters will hang on to smog longer, as will areas where the pollution is trapped by a particular landform. The numbers on the dots in the figure shown are just identifiers, but the colors will indicate very different half-lives. In southern Arizona, for example, see the dot labeled 70, where the half-life is between 0 and 2 hours. And the half-lives near Atlanta, 47, or Columbus, which is 51, where it takes 5 to 7 hours for the nitric oxide to be precipitated. This plot shows a similar range of half-lives in China. So why is the half-life so different in some areas than others? And why is it so bad in some areas? A frequent reason for long half-lives is the artificial concentration of pollutants by temperature inversions. Under most conditions, during the day, solar radiation primarily passes through air and hits the Earth, which is warmed up and in turn warms up the nearest surface. That warm air will rise and will spread pollutants to where they are less concentrated and shorten the half-life of the smog. However, under particular conditions, cold air can move in below the warm air, and that prevents convective currents, the ones that will bring hot air up, and it traps pollutants near the surface, where they remain concentrated. Temperature inversions commonly occur in lowlands, where the cold air from higher elevations sink down into valleys overnight, or in maritime areas, where cooler ocean air blows in overnight and gets caught against the inland elevation. It's of course particularly special when you get both, like in Los Angeles. This picture shows not Los Angeles, but another particularly drastic inversion and the associated smog in Almaty, Kazakhstan. So again, smog forms most readily in lowlands, check. Smog also forms most readily when there's a source of pollution, often people, check. Here's the part that might not be immediately obvious, but really actually matters. Historically, people have inhabited lowlands and marine environments far more readily than other areas because the water is essential for life and makes transport so much easier. You're likely to find rivers in lowlands, and you're likely to find marine environments next to oceans. Oops. And just in case it wasn't clear, the increased presence of reactive oxygen species is terrible for human health and has been linked to increased incidences of asthma, among other things. That stuff is bad for you. But reactive oxygen species are also really hard on many materials, including any alkenes in materials like those of synthetic butadiene and natural rubbers, which undergo ozonolysis and break into pieces. Plant stippling can also result from high ozone levels. Remember how we said most organic compound color comes from conjugated systems of alkenes? Well, the chlorophylls of plants are colored, which helps them to absorb visible light. And although some of the color also comes from magnesium and nitrogen charge transfer, they're vulnerable to oxidation by ozone, and some plants more than others. This often results in the destruction of the chlorophyll in an area that doesn't cross leaf veins, which is observed as small miscolored dots, again called stipples. As you might imagine, since chlorophyll helps plants get energy from sunlight, destroying the chlorophylls is not so helpful for the plant. Mobile sources are named by the EPA as about 50% of the source of nitrogen oxide emissions, with power plants being only about 20% of the source and all other sources making up the remainder. Cars are a notable source, not just of nitrogen oxide, but also of smog-perpetuating hydrocarbons from incomplete combustion. There are many sources of hydrocarbons in an internal combustion engine vehicle, including the lubricating oils vaporized on the hot crankcase of the engine, and of course also the exhaust. Older engines had a carburetor to inject fuel and air mixtures to the engine, and this could actually leak out gasoline vapors, which would also be a source of hydrocarbons. Some of these emissions are controlled by using different temperature formulations for fuels. So, example, the gas that you get here in Chicagoland around October is lower boiling than you'd get in the same location in July. But modern vehicles also use fuel injection systems that will also reduce carburetor emissions drastically. Even so, exhaust emissions are substantial. That's because an internal combustion engine has a paradox. It can be optimized to completely oxidize hydrocarbons by making sure more oxygen is available, but it also produces more nitrogen monoxide in this case. You can see on the figure, as you increase the air to fuel ratio, as you have more oxygen, hydrocarbons go down, so does carbon monoxide, but nitrogen oxide goes up. Understanding the 4-cycle engine helps to explain why. The first 2 cycles in an engine are the intake, where the air and fuel are introduced into the cylinder, and then the compression, where the volume is reduced prior to ignition. The more compressed the fuel-air mix is, the more efficient the combustion is. You get more contact. But that increase in pressure also increases temperature, which can cause premature combustion, things burning before they're ignited, and it also can cause more oxidated nitrogen, more NOx species showing up. In the 3rd cycle, which generates the power, the fuel-air mix is ignited and the chamber rapidly expands. However, while any nitrogen monoxide formed would normally start to decompose to molecular nitrogen and oxygen as soon as it contacts another molecule, that only really happens at high temperatures, and the expansion of the chamber cools the nitrogen monoxide quickly and traps it in a less stable form. In the final stage, everything that's formed is exhausted, which will include carbon dioxide and water from the combustion, necessarily, but it will also include unreacted nitrogen gas from the atmosphere, incomplete combustion products like carbon monoxide and other hydrocarbons, and of course, nitrogen monoxide. Your text details a whole host of engineering to engines that has helped engines to become more efficient, which also typically means that the fuel hydrocarbons are more completely oxidized. It's worth a look if engineering and engines are kind of your thing. These engineering accomplishments are pushed by emissions controls legislations and fuel efficiency standards. 1970 and 2008 marked significant legislative actions, with continued reductions as part of the 2008 legislation, which was repealed sometime around 2016. So if you think about how smoggy LA can be, but now imagine it without the emission standards, when the emissions of hydrocarbons and carbon monoxide are nearly 20 times as high, which you can see in the table shown. Vehicle standards aren't just about vehicle efficiency and reducing climate change and emissions. They're also about ozone and human health. Humans are the source of most problematic levels of hydrocarbon emissions and nitrogen oxides and other smog-forming pollutants. But these compounds also may be formed naturally. Nitrogen oxides are formed by the action of soil microbiota. Both nitrogen and sulfur oxides are formed by volcanic activity. And even the hydrocarbons can be produced naturally, particularly as terpenes like isoprene, which are produced by most plants at some level. These compounds are actually greenhouse gases in addition to smog-forming pollutants. But they typically don't form smog in forests if there isn't also appreciable nitrogen oxide for the terpenes to react with. They do eventually react and degrade in the upper atmosphere, in the stratosphere, because even if there isn't ozone in the troposphere, there should hopefully still be ozone way up in the stratosphere. That's the dream. That's the dream.